or no, 1.5, Let's talk about the most important parameter what we use in fired heaters, and that is the radiant heat flux. Radiant heat flux is radiant heat duty divided by the surface area. So radiant heat transfer per square foot of tube surface. And why do we need to define this or control the flux? Because we are processing hydrocarbons, and hydrocarbons are very sensitive. So as the film temperature goes up, the coking rate goes up, and when the coking rate goes up, the run length of the heater goes down. So we want to make sure that your heater runs for a certain amount of time. It could be 2 years, it could be 4 years, it could be 8 years. I don't know. I mean, but basically everybody wants their heaters to run forever. So as a guideline, lower heat flux is better for your heater. But you also need to watch out that lower heat flux means bigger heater, more money. So there is always a balance between the two. So this is a guide, average guide for heat fluxes and mass velocity. And I have a thumb rule. If you don't know the flux you want to go with, just use a number which is very, very safe, is 10,000. I mean, most of the time, if you go with 10,000 flux, you won't go wrong. I mean, if you have a special heater, then it's different, but 10,000 flux is a pretty decent number for most of the refinery services. Other thing you want to specify is the mass velocity, and we have some guidelines over here. I do want to talk about another equipment, because most of the technology in fired heaters has come from boilers. Now in boilers, we are heating water, and water is an excellent conductor of heat. So we are not worried about coking or film temperature. And there, sometimes we use fluxes as high as 45,000 BTU per hour foot square, actually. That's how fluxes go up in boilers. So 100 million BTU boiler may be 1/3 the size of 100 million BTU heater, So very, very different approach. So another thing which we want to control for uniform heat transfer is H by D in vertical cylindrical heater, or H by W in box heaters or cabin heaters. API 560 gives maximum H by D of 3 for VC heaters, and they have now gone up to 4. Both numbers used to be 2.75. My recommendation is don't exceed 2.5 or 2.2. I mean, the lower the better. I mean, the lower this thing is, lower you will have maldistribution of heat flux, because the heat flux at the bottom and at the top is going to be very different. In fact, it's going to be highest at about 1/3 the height. So there are a lot of factors which come into this thing, but try to stay away from very tall, narrow heaters. So let's talk about a very common design for refinery heaters, and that is a horizontal tube box heaters. Very good design, and generally the tubes are on the side. We can put tubes in the roof, and we have a long convection section. We have burners in the center. Good design, actually. We use it very often, and you will see mostly crude heaters, vacuum heaters will be in this configuration. And historically, the tubes have always been horizontal in the old designs of heaters, and in the new designs, we have the vertical configuration. So here is a configuration of vertical cylindrical heater. very popular design. It's a space-saving design and cost-saving design, and then in vertical cylindrical heater, you are going up and up. So there is the space is consumed is very little. We use only few burners. The convection section is very compact. So that overall cost of a VC heater is 10 to 15% lower than a cabin heater, And the reason we are talking about this is that in our project, what we are talking about, we had a very tight requirement of the space. So the client said, I have to put this heater in an existing unit, and we only have 80 feet by 50 feet. That's all we have. And I still want my air preheater. I still want a fuel gas skid in this place. I want ammonia injection grid skid, ammonia injection skid for the SCR also in this place. So that's all I have. And if you can fit a heater, we want to see how will you design. So I will show you what we designed, later actually, but we came up with a unique design of air preheating system, and that's how we saved the space. But anyway, let's talk about what can we fit over here in terms of whether we can fit a box heater or whether we can fit a vertical cylindrical heater, So one thing about box heaters is when you put horizontal tubes, whatever tube length you have, you need an equivalent amount of space, empty space, for removing or pulling those space tubes, So that's called a tube removal space actually. So that is becomes you require a lot of space for box heaters, So here we started, the first thing we said, okay, what is the rate difference? Split between the radiant and convection. And generally, as I said, 60 to 70% is absorbed in the radiant section and remaining 30 to 40% in the convection. So we are assuming a split of 66%. This is come up from the computer, even though we may start at 60 and then go to 66, or start at 70 and go down to 66. So depending on whichever way we go. So it shows you 66% heat duty. So radiant heat duty is 0.66 into 126 is about 83.2 million BTUs. That's what our radiant heat duty is. And then we selected a heat flux of 10,000. So once we select a heat flux, we know how much surface we have to provide. We take the radiant heat duty divided by 10,000 is 8,320 foot square. Very simple calculation. We are not doing hi-fi calculations as yet. We are just doing simple arithmetic calculations. So we need to provide about 8,400 square foot of heat transfer area for this radiant section. Let us see how we can provide that surface. So as I said, when we talk about radiant section, and radiant section is the most important section, we also have to select the tube size and the number of passes. And I have an option to select a 6-inch pipe, a 5-inch pipe, and a 4-inch pipe. What is the difference? If I select a 6-inch pipe, I will have fewer number of passes, and operationally, owners prefer fewer number of passes because then they have to do less pass balancing. If you have a 4-pass heater and if you have an 8-pass heater, you will see 8-pass heater is really difficult to control as compared to 4-pass heater or a 2-pass heater. So larger tubes give you more reliable operation. But at the same time, as the tubes become larger, they become thicker. So as they become thicker, they need more metal for the same surface area, so they become more expensive. So a heater vendor, and I'm a heater vendor also too, so don't get me wrong actually. We always start with a 4-inch pipe. We will try to give you a 4-inch pipe because 4-inch pipe is the cheapest in the industry. So we always, when we are designing it, our first instinct is to use 4-inch pipe. So we had an option of 6-inch pipe, 5-inch pipe, and a 4-inch pipe. 3 pipes size we selected, and let us see how they come up with. So our option is how many passes will be there, and how can we collect the total tube length. Total tube length is very simple. We have the total surface area divided by the surface area per foot, and that will give us how much pipe we need. So I have selected 3 pipe sizes, 4-inch, 5-inch, and 6-inch. These are the ODs. This is how much surface they have per foot, linear foot, 1.178, 1.456, 1.734. So if I'm going to be providing 4-inch pipe, I will be providing 14,000 total tube length. A 5-inch pipe will be 11,000. 6-inch pipe is 9,589. And this is a very familiar pressure drop equation for calculating pressure drop. F is a friction factor, G is the mass velocity, ST is the specific gravity, D is the diameter, So it's very simple equation. We calculate the pressure drop and we come up with this thing. So I take the total mass flow rate, 1.8 million pounds an hour, and I select 4-inch tubes. I come up with 4 passes. My mass velocity is very high, 1400. I go to 6 passes. My mass velocity is still very high. If I go to 8 passes, my mass velocity will still be very high, 700. So I may end up with 12 passes to handle 1.8 million pounds an hour. So we decided 4-inch pipe is not the way to go forward. Then we went to 5-inch pipe. Again, with 4-inch pipe, the mass velocity is 900. 6-inch is about 600. I may have to go to 8 pass, and even 8 pass will be, 400 or something. So we said, okay, let's go back. So then we went to 6-inch pipe, and we looked at, with 4 passes, we get a mass velocity of 623. With 6 passes, we get a mass velocity of 415, which is pretty decent, And all these mass velocities, we have to see what is going to be the pressure drop now. So we do this pressure drop calculations. Very, very simple. Don't get scared by these numbers. Process engineers always have these things. They come up with this delta P log mean. And then they say, okay, 4-inch, 4 pass, the pressure drop is 620. Allowable pressure drop is only 40. So what will we do? 6 pass with 210, they are rolled out. Even 8 pass will be high. So 5-inch, okay, we get 170. 6-inch, 6 passes, we get 55. 4 pass, we get 60. 6 pass, we get 20. So we selected the 6 pass configuration, 6-inch, 6 pass configuration, because we had an allowable pressure drop of 40 psi. And I will tell you what we did with the balance 20 psi, So I'll tell you later, but that's what we selected and went ahead with. So our thinking was, okay, we have 83 million BTUs, 10,000 flux, 8,300 square foot area, 6-inch tubes, 12-inch spacing, 2D, 4,800 foot of pipe is what we have to provide, So with this configuration, uh, we looked at the horizontal tube. We are kind of showing you that if we had to do horizontal tube heater, we will have to provide a tube removal area, which is the same space. And we, as I said, we needed space for air preheating system, fuel gas skid, ammonia injection skid. So it was impossible to put a box type heater, So we said, okay, we will select a vertical cylindrical heater for this application. So even in vertical cylindrical heater, I am showing you three options. So we can have 72 tubes, we can have 84 tubes, we can have 96 tubes. You can see the number of tubes are multiple of 6 and 2 because we want to have even number of tubes for each pass, and there are 6 passes, so we basically have a choice of 72, 84 and 96. When we do that, we get effective tube length of 67, 57 or 50. And we look at the tube circle diameter 23, 27, 31 and H by D of 3, 2.2 or 1.6. So anyway, if we have a tube circle diameter of 23 or 27, I think we can definitely fit it in our plot space of 80 feet by 50 feet. So we move ahead. That I will show you what we mean. So this is the first design, which is H by D of 3. So 72 tubes, 68 foot length. So we looked at it, but we did not like it. We found the burners are very close to the tubes. We don't want to give this heater. Although higher the H by D ratio, lower is the cost. A tall, narrow heater is always cheaper than a short, stubby heater, So, I mean, if I wanted to save money, we could have given this design, but we decided against this because we didn't really like it. It was violating API requirement also from that time. Now they have relaxed it. So the second option was go with 2.2 H by D ratio and number of tubes of 84. So the diameter becomes about 27 feet, the tube circle diameter. So we looked at this option. And the third option was go to 96. Now that was becoming like a very short heater. It would be good, but it is more expensive. So we decided, let's not go for this, select something in the middle and move on. So we selected the B design, but here what they are trying to show you is what is the process for sizing the radiant box. So once we know that how much tube length we have to provide and we know the number of tubes, so we get the effective tube length. And then we do this minor adjustment of the return band and we get the straight length. The straight length is about 65 feet. Then we take the return band height, clearance from arch, clearance from bottom to this one, including the expansion and creep. So we take that into account. And we come back with the total height above about 68 feet. So, and the diameter is about 24. So we have, L by D of 3. I mean, we could have sold it actually, we could have given it, but we decided to give them a better design. So we selected option B, which was also giving us good floor heat flux of 247, API says 300. So we basically went with this type of design actually. So as you can see, there are so many options. We have the coil size, the coil height, the number of tubes, and then we have the burner layout. And the burner layout, we want to make sure we don't go with very high heat release burner. Flame height should be less than 60% of the firebox height. And we want to make sure we have adequate burner to burner and burner to tube clearance. This is a 3D model showing our inclined firing technology, what we have for fired heaters. So this is what we had to do with. So the heater firing rate is about 138. We selected 12 burners. Each burner is about 11 feet. We calculated the burner circle diameter. So with that, we calculated the minimum required clearance as per API of 6.6. So the minimum TCD required is about 25 feet. Actual TCD is 26.7, So we kind of optimize the number of burners, the heat release, the firebox dimensions. So we do all this, several iterations, and we try to see which will give you the best and most optimum design, because we are always competing with other vendors, so we want to be cost competitive as well. So we have to make sure that we offer you the optimum, and this is what we came up with in terms of the burner layout and the tube layout. This is the outer circumference of the heater, the wall. Then we have the refractory lining, and we have this tube 84 tubes over here, and then 12 burners over here. We came up with a 12-foot burner circle diameter. The distance between burner to tube is 7 foot 5 inches. So we are very generous in terms of finding, clearances. So we give a very good, robust heater design actually for this service. Another important thing which we have to do when we are sizing the radiant section is to determine the convection section layout, because some amount of radiant heat is transferred to the bottom row or the bottom 3 rows of the convection section. So we need to determine, and here what we do is we want the convection section to be supported by the radiant section. So the way we do it is all 4 corners should fall on the radiant section casing. So we know the firebox, this thing, and we can, if we know how many tubes we are putting, we can get the length of the tubes. And we try to see whether we can get a mass velocity, flue gas mass velocity of about 0.3 to 0.4 pounds per second foot square. So that's what our objective is. So since we had a 6-pass design, we went with 6 tubes per row, and the convection section width is about 6.5. So we can calculate the length of the tube by using Pythagoras theorem. And that's what we came up with actually. So we did it. So I think I want to stop over here and see if you have any questions or if you have any, things we can answer it. The reason being, I mean, if you want, we can start on the Stephen-Boltzmann equation, but if you have any questions, I'll be more than happy to answer it. But okay, let's keep on going. So this is the Lobo-Evans method, which has been described by Lobo and Evans in their clarifications. And it talks about radiant heat transfer is a function of several parameters. First one is the radiation component. This is basically the Stephen-Boltzmann this thing. And then this is the convection coefficient, 7 into Tg minus Tt, So that is the convection coefficient. And then based on the fire heater geometry, we have these three parameters. One is the effectiveness factor, alpha. ACP is the cold plane area. And then F is the exchange factor. So exchange factor is depending on the gas emissivity. Uh, then the partial pressure of CO2 and water vapor, and the mean beam length of firebox. So these are the three parameters which we will be calculating in our next webinar to calculate the exchange factor. And then we will be solving for this equation. Now, one thing I want to talk about, since we have a few minutes left, that the radiation in Lobo Evans correlations does not depend on the flame or flame color. A lot of people talk about flames and flame color, but no radiation component is taken there. We are going by the partial pressure of CO2 and water vapor. These are the two molecules which are triatomic. And these are the ones which are responsible for radiation of heat from these molecules to the tubes. So that's what is dependent on, And we will look at more, and then mean beam length. Mean beam length is the basically the length, the breadth, and the height, the three factors which we have. We use that to calculate the mean beam length of the firebox. So we will work on all these parameters in our next webinar, and we will solve for this equation and then come out with the details of the radiant section heat balance. So that's what we are solving. And if you have any question, please send it to us, and we will be more than happy to come back. So we will start with this convection section, radiant section. We will do all these calculations in detail the next time. So let me know if you have any questions. I'm more than happy to answer these questions. So I have received one question from Ganesh. Which factor affects the bulging of radiant coil? So bulging is mostly caused by high tube metal temperatures, or I should say basically from flame impingement, It may not be visible flame impingement a lot of times. It could be the hot flue gases also licking the tubes, So high tube metal temperatures or coking or bulging is the biggest enemy of heater operators. Once you have this cycle forming up, it will be endless, and you will have to either replace the tubes in case if you have bulging, you don't have any other choice. But most of the time it is caused by high tube metal temperatures. And we have a very good technology for solving this bulging of tubes, and which is inclined firing. In inclined firing, what we are doing is we are inclining the flames away from the tubes. And when we do that, it makes a very big difference and lowers the tube metal temperatures by about 100 to 150 degree F. We have done this in two crude heaters, one at Valero, and that heater used to have shutdowns every year, almost every year or so. And after we put new burners and inclined the burners, that heater has been running for more than 5 years. So it's a very, very simple technology, and it can be done in almost every this thing. So is inclined firing compliant with APFA 60? Yes. I mean, there is nothing in APFI 60 which says you cannot do it, I mean, and we have done this in about 15 heaters. I think 6 are in India and 9 in US. And it is our default, in all our new heaters, we are putting inclined firing, and it is the way to go, So it does give us a lot of benefits, It makes sure that there is no hot flue gases uh, touching the tubes or hot flames touching the tube, And you still get the same heat transfer. In fact, you get better heat transfer. You get a lot better heat transfer, and we can show you. You can see some of our presentations or webinars on inclined firing, and you will see it is Okay, I got a question. We say the higher adiabatic temperature, higher would be the radiant heat transfer. Yes, Siddharth. If you use air preheat, when we use air preheat, what we are doing is we are increasing the adiabatic flame temperature. And when we increase the adiabatic flame temperature, the more heat transfer takes place. I hope I'm able to answer your question. All right, guys. Thank you very much. It was a pleasure doing this webinar, and keep on sending your questions. The more questions you send, I do want to tell you something. We had almost 135 people registered, and we had, I think, about 50 questions which we have received. So we will try to answer some of them in our next webinar. Thank you very much. Bye.